So what it is very important to remember is, because limits stress people out, they are really algebra problems with limit written in front. Okay, if I take this away, algebra, oh, now it's calculus. Now it's algebra, now it's calculus. Do you see what I'm saying? So just calm down is the first thing I'm going to say. We're going to look at this first one in a table because they do like to put questions with a table on the AP exam. And so I like to show it to everybody. Instead of having you all get a calculator, we're just going to follow along with what I'm going to put up here. So I'm going to go and put that function into y equals. And so I'm going to just have you guys watch for the sake of time here. Okay, so I put that in there. I want to go to my tables set, and we're going to be centered at -2. So I'm going to start it at -2. And that delta table, do you know the triangle, the delta, the Greek letter delta? That means change in. So that is what you want to count by. So I'm going to count by 0.5. I'm going to count by halves, go to my table, and we can start filling this in. So at -2, what does it say there? Do you see that? Error. So you can go ahead and write error in your table for -2. But what we're going to do, and the idea of what goes on in this table, is that we're going to zoom in on that point -2 from each side. It's like, do you know how when you have a microscope in science class, do you ever use that and you like zoom in on, or like you can change the power of it? Anyway, that's kind of what we're doing here. So at -2.5, it says -1.4. And then at -1.5, it says -0.714. And just bear with me with going through this, because again, they put tables like this on the AP exam. So I want you to see it visually what's going on. I'm going to go back to my table set, recenter it at -2. Now I want to bring it in. We're going to zoom in on that point. What do I want to count by now to get these two? 0.1. So instead of 0.5, I'm going to count by 0.1, go back to my table, and then there's the numbers that we get. So -1.069 on one side. I apologize for the glare. There, I'll put it over there. And -0.935 on the other side. And then what would I need to count by when I go to my table set for the last two? 0.01. So do you see how we're making the increments smaller and smaller? We're zooming in on it. So you have to like imagine super, super tiny numbers. It is difficult. You know how like our brains really can't do infinity, like gigantic numbers? It's the same thing, but kind of opposite. It's hard for us to understand super, super tiny numbers as well, but that's what we're trying to do here. All right, so we got -1.007. And then on the other side, -0.993. And here's our error. So as you look at these numbers, here's the whole point. What are these getting closer and closer? I know that there isn't anything there. There's a hole, right? But what are you getting closer to? -1 on both sides. So the answer to this limit is -1. There is an answer, even though there's a hole there. And here's the explanation that I always use. Have you ever been walking up the stairs and you're not paying attention and you get to the top of the stairs and you take another step anyway and you stumble and you drop everything and all your friends laugh at you? Do you know what I'm talking about? Like you take another step even though there isn't one there. That's like a limit. Even though there's not a step there, if there had been, your foot would have landed right on it. It's the behavior of the graph, not whether something is actually there or not. Are we together? How did we find holes in graphs before calculus? Like pre-calc? What cancels out? So just real quick, if you factor this, we'll review our factoring. How's the numerator going to split? At 1 and 2, it'll be, +2 minus 1. And then down here, actually, I think I did this exact one with you guys last time because I'm remembering the 2 and the 5. So what cancels out? And that means that the whole will be at -2. How do you get the other part? Plug it in. Watch this. -2 minus 1 be -3. And then down here, -2 plus 5 is 3. Oh my gosh, it came out to -1. Isn't that crazy? okay? But it doesn't matter that there's a hole, it's where the graph was headed. So in order for a limit to exist, the same value is approached from both sides. If one side goes to one place and the other goes to another, then there isn't a limit. We would say DNE, the limit does not exist. I always bring this up just because I think it's funny, but the more time that goes by, the older and older the movie gets. But have you seen or heard of Mean Girls? You know, she goes to the math championship at the end of it, and she's like, the limit does not exist, as though it only like just occurred to her. If you look behind her, the graph has an asymptote in it. It's like, if you understand the math, it's a really funny scene in the movie because it's like, she's like, the limit does not exist, like it only just occurred to her. All right, the graph cannot increase or decrease without bound, is how we say that. What do you think without bound means? Like, what does that mean? Means what? Just the words without bound. But it'll go on forever, okay? Without bound means going on forever. So like you're looking at an infinity situation. There is an exception to this. It's except for the one-sided limits. You can get an answer of infinity or negative infinity if it's only from one side. So, that's like the one exception to that. So you can get an infinity or negative infinity answer if it's one-sided. And then the last one, the graph cannot oscillate. And I'm going to type one in here just to show it to you on the calculator real quick. For what I mean by oscillate, and also they just kind of look cool. I'll type that right. Oh, not in radian mode. There we go. All right, so here's an example of what this will look like. Do you see how in the middle it did a like kind of a heartbeat machine kind of thing? I'm just going to keep zooming in on it just so you can see it. Yeah, isn't that like weird? Here, I'll zoom in again. It's like oscillating means it can't make up its mind. It like jumps back and forth rapidly. If I zoom in again, it's going to just look like a barcode. There's no overall behavior there. So we say the limit does not exist, but that's what oscillating is. And it just looks cool. So I always love to bring it up. For these, they're going to go really quick. These are no work questions, which should make you happy. But you're going to have to watch me point to stuff because I don't really have better explanations than look. There's the answer. Okay, so you're going to have to look at this. And remember, it's behavior, not what's actually there. So we're going to use this graph. Limit as x approaches -1. So you want to look at -1 and only -1. You want to cover up everything else except -1 and like zoom in on that point. Where are both sides headed to -1? 0 is the answer. That's it. That's really all that we're doing. All right, but both sides have to come together. They have to meet up. All right, limit as x goes to 1. So I'm going to cover up everything else except 1. Watch me point to this. Where are both sides headed? I know there's a hole, but it doesn't matter. It's where are they headed? -1 is your answer. It's just the behavior of the graph at that point. This one is what we call sided. It's -6 from the positive side. So -6 from the right. So here's -6. We're only looking from the right. So where is that graph going? Negative. So you can put -infinity since it's only from one side. It's only for one-sided limits. So this one, -6 from the negative side. So -6 from the left is also -infinity. But if you look at -6 overall, I realize both sides are going down, but are they ever going to touch and meet up? No, so you still have to say does not exist. The infinity and -infinity, again, it only works for one-sided. So we're going to do the same thing around -2. Look from one side, look from the other, and then look overall. So -2 from the left side. So here's -2. You want to only look from the left. So watch me point to it. I know there's a hole there. Bless you. But if there wasn't a hole, the graph would land right on what? Yeah, -1 is your answer. And then -2 from the right, you're going from this side. What does it land on? Can we call that 2? I realize it's a little above 2, but like, can we just go with it that it's 2? Yes. And then what is limit for -2 overall? Why would that be does not exist? They don't link up. So from one side, it's -1. From the other side, it's 2. We're going to talk about this when we flip the paper over, but what kind of discontinuity is that? It's a jump discontinuity. Good. All right, limit as x goes to -infinity. That's welcome back to algebra 2. That's your end behaviors. So we want our left end behavior. Where's this left end leveling off? 0. Will it ever touch 0? No, it's behavior. And then limit as x goes to +infinity. Where's it leveling off on the right side? -2. I kind of like these. You just look at it and say the answer. All right, the next one, the series of these, I like to put them together so you can like kind of make comparisons. We're going to do 4 from the left, 4 from the right, 4 overall. So 4, there's an asymptote. From the left side, where does it go? -infinity, and you can put that because it's only from one side. 4 from the right is +infinity. And then 4 overall does not exist. You want to look at 4 where the asymptote is. But no, and I'm not joking. Literally take your hands. Like if it says 4, find 4, literally take your hands and do this. Because these graphs are wacky. There's arrows everywhere. There's a lot of like noise that you have to kind of ignore. So literally just take your hands and cover up everything except the one x value you want to look at. All right, and then what are these last ones I got here? -5 from the left. So -5, it would be right about there. What do you guys think? Yeah, can we call that -2? Like close enough. And then limit as x approaches 5. I get that there's a hole there, but pretend there's not. What are both sides going towards? 0 is your answer. Again, it's just behavior. If you zoom in on that point, both sides are going to 0. So again, limits are behavior. What you're being asked for in this next section is an actual functional value. So this is calculus. Now we're back to algebra. Is there actually a point there? There has to actually be something. It's not all that touchy-feely like behavior stuff anymore. Now it's, is there something there? So f of -2, do we have an actual filled in point? At 2, or we're going to call that 2, close enough, like where the actual filled in point is.
So does the whole just not matter in that instance?
Yes, because we want where the filled in one is, because it's where's the actual point. All right, -6, what do you think? Yeah, asymptote, and we would just write DNE. I keep moving the paper up and down, but you guys have it in front of you, so just look at it. F of 1, this is the haha trick to do the point somewhere else. Now, where is the actual point? It's 4, good. All right, f of 5. There's a hole, so you would write DNE. All right, 4, I think, was an asymptote, wasn't it? Yeah, because we looked at that one. So DNE. F of 0, so the actual point for 0. -1, good. I do get asked this sometimes, but Miss Cole, I don't see an actual filled in point there. Like, there are points everywhere that, like, I mean, there's a point here and a point here. Do you get what I'm saying? Like, the graph is a series of points. There is a point there just because it's not bolded, still a point. All right, and then f of -1 is 0, good. So these were limits, that's behavior, that's just where is it headed towards. This is there actually a point there? we'll keep going a little bit. I'll give you a break here at some point, but we'll keep going because we didn't do too much yet. So now we're going to talk about continuity. This definition for continuity will come up on the AP exam, probably on the free response card. They love having you write out this definition and explain it. Maybe put some stars next to it, okay? There are three things. For a function to be continuous, add a value C. When we do an actual problem, C will be a number like 3 or 5, okay? But right now we're just going to call it C. In order to be continuous, first of all, there has to be a point. F of C exists. There's a point. There has to be something there for it to be continuous, right? So there has to be a point. F of C exists. There has to be behavior from both sides. Like if you zoom in on it, both sides have to come to the same place. Like you can't have a jump, right? So the limit has to exist. Limit as x approaches C of the function exists. So there has to be a point, there has to be a limit, and they have to agree. They have to equal each other because otherwise you get that floating point situation where there's a point and there's a limit, but they don't equal each other. Writing this one out always bothers everybody, so watch me point to this. If I cover up these words exists, if you take this and slap an equal sign in between them, that's all it is, okay? You want the points to equal the limit. So there is a point, there is a limit, and they equal each other. They agree. So that's your definition. That will be on there 100%. So we're going to write out the ways that you can break those rules. So your types of discontinuities and the vocabulary of what they're called. So let's try and break the first rule. There's two ways you can break this rule. How can you not have a point on your graph? A hole. Okay, so you could have a hole in the graph. And that is called removable. Because you just removed the point. So that's the first rule getting broken. And there's another way you can do that. What's the other way you could not have a point? Perfect. Okay, so if there's an asymptote, but that's like a more deep-seated problem. You couldn't fix it just by putting a point back in there. So that is non-removable. And specifically, it's called infinite. That's an infinite discontinuity, which should make sense. The arrows are going up forever. So it's called non-removable, but specifically an infinite discontinuity. So those are the ways you can break the first rule. Now we're going to break the second rule. How could there not be a limit if there's a jump? So if you have something like this. Now that is called a jump discontinuity, but would it be removable or would it be non-removable? Non-removable. You can't fix it just by putting a point back in. So it's non-removable, but specifically we call it a jump. I think those are the easiest ones to identify because it literally jumps. Like you can see it very easily. And then how could you break the third rule? So there's a point and there's a limit, but they just don't agree with each other. Yeah, like the floating one that's like, haha, I tricked you. The point's over here now. So you actually have a point and you have behavior. Both sides are headed to the same place, but the point is somewhere else. That is also removable because you just removed the point. So what I'm going to do for this next section is, unfortunately, if you were not here and you're watching this at home, I'm going to leave this projected up there and write these answers on the board so that you guys don't have to keep flipping your paper back and forth. Okay, so unfortunately, I am going to pause this recording, and if you're watching from home, you are going to miss this next section, but I'll take a picture of the notes and you'll be able to fill in the answers. So these last two are making the function continuous. If you want the piecewise function to be continuous, the two pieces need to meet up. Pep talk. If it's a multiple choice question, is anyone checking your work? No, so you can just do the problem however you want. If it's free response, They want you to use correct limit notation and talk about this entire definition of continuity. I'm the messenger on that one, okay? So I'm going to show you on this problem how you would write every last tiny little detail that they want to see. On this one, I'm going to let you just skip that and answer the question, okay? So for continuity, you need a point. So let's find our point at -1. G of -1. I almost wrote F, but this is G. G of -1. Which piece of this are you going to plug -1 into? Like which one has -1? Good. So if you plug in -1 for X, you get -1 minus P. So we just plugged in -1 to the correct piece of the function there. So that's the point. Now the limit, you have to do it from the left and the right. They want to see this notation. Again, I'm the messenger on this. So we're going to do limit as X goes to -1 from the left of G of X. And I'm going to go ahead and write the other one at the same time. Its limit as X goes to -1 from the right of G of X. I would just write them both at the same time. Like they want to see all this notation. But all you have to do is plug -1 into both pieces of the function. Like what you're actually doing isn't that hard. They just want to see all this writing, okay? So you're going to plug -1 into the first one. -1 squared is 1 minus 2 is -1. And if you plug -1 into the second piece of the function, you again get -1 minus p. They want to see all that, but really all you have to do is set them equal. If you want them to meet up, you're just going to set this equal to this and solve it. When we do this one, that's all we're going to do. I'm going to skip all the writing of everything. So you're going to take -1 and set it equal to -1 minus p, and then just do the algebra to solve that. This happens all the time on the AP exam, is that the math you're actually doing is like nothing, but they want all this writing. So anyway, what would you do to start solving them? Yeah, you would add 1. That gives you 0 equals -p. You would divide by -1, but 0 divided by anything is 0. So if it's free response, you've got to write all that. If it's multiple choice, no one's checking your work, just go ahead and set them equal. And that's what we'll do for this one. We want to make the function continuous at 4. So you're going to take the first piece of this, p squared minus 2p plus x, set it equal to the other piece of the function. So you're just setting them equal. And then you're going to plug in 4 for x. So everywhere there's an x, you're going to put a 4. So what would that actually give you on the right side if you plug in 4?
16.
And then plus 3 will be 19. All right, so welcome back to Algebra 2 class. We do this in pre-calc as well, though. What would you do to start solving that one?
Oh, factor.
But first,
Evacuate.
evacuate. That's what I call it. Evacuate, evacuate. Get everyone to one side so it all equals 0. Everybody out. Evacuate. So you're going to subtract the 19. So that'd be what, minus 15? Evacuate, evacuate. And then you're going to factor. So we're going to get 2 answers for this. 15 is going to split 5 and 3, and then what symbols? Perfect. And so your answers, you're setting those equal to 0. So you get p equals 5 and p equals -3.